Thank you very much, everybody, for attending in our graduate seminar series. We do really appreciate David Hampton for joining us, Reservoir Engineering Technical Lead, Permian EOR, Oxy. Let me just, David, I'll give a couple of details about you before you get started. We do appreciate you making the time to visit us and share your knowledge and expertise with our graduate students. David Hampton is the technical reservoir lead for Occidental Petroleum's onshore resources and carbon management. He is a professional reservoir engineer, experienced in project management and field development planning, considered an expert in improving injection operations and ultimate oil recovery through water flood and EOR processes, miscible gas injection and chemical, successful leader of a variety of field development projects using procedures that confirm design philosophy, minimize risk, and optimize recovery. He holds a BS in petroleum engineering from the University of Texas and an MS in petroleum engineering from the University of Houston. David, thanks a lot for joining us. The floor is now yours.
All right, my pleasure. Thanks. All righty, I'm going to share my screen and actually turn off my, let's see, okay, there we go. All right, and lost my icon here. Just give me a second. There it is. Okay, does that work for you guys?
We see the slides.
Okay, great. Okay, so thank you so much for inviting me, and pleasure to get to visit with y'all today. I'm going to talk a little bit about forecasting for carbon capture and utilization sequestration, EOR performance. I wonder, let me, there we go. I think I can get that there. All righty. So goals are an amazing concept. It gets the whole team pulling towards the same objective. Just like John Kennedy's goal to put an American on the moon years ago, I'm sure all of you have goals. A lot of you probably completion of your next degree. But beyond that, I found that it's good to set goals each week and daily to help me focus on what work is important. The picture here is Vicki Hollub, our CEO, and recently she set a couple of goals for us toward carbon neutrality. And the goals are set are that we're targeting to be net zero emissions associated with our operations by 2040 and net zero emissions associated with the use of our products by 2050. So that's a pretty aggressive stance, but I think, you know, we certainly have the technology, the ability to get there. It's just how much of that we'll be able to accomplish. Okay, so typical CCUS goals is to sequester 99% of the CO2 that's injected, but to be economic, we need a CO2 utilization around 6 to 12 MCF per barrel of oil. And that's really gross barrels. Many times when we look at utilization, we actually are using net barrels or barrels that are only EOR barrels, and that raises our metric a little bit above that. But if we include the water flood or the prior barrels, the prior decline, we can easily get to this 6 to 12 MCF per barrel. The IEA estimates that 200 to 400 billion barrels of oil could be recovered with CO2 EOR if the sources were sufficiently available. And net emission savings could range from 50 to over 150% from processes that are using non-fossil source CO2, where the CO2 or the stored CO2 exceeds emissions from production, and the use of the oil can be thereby net carbon negative. Okay. So this is a graph, the graph over here on my right is a graph of domestic U.S. oil production by EOR type. This is actually from Penwell, and really the last data that they had that was accurate was 2014. But what you can see here is the red is thermal, the blue is our CO2 miscible EOR oil. The darker gray through here is non-miscible CO2. And then the lighter gray is gas injection that does not include CO2. So that would be primarily the North Slope. And what we can see here is that in 2016, the domestic miscible EOR is about 300 MBO per day. And of that, oxy comprises about a third of that. And CO2 EOR comprises about 40% of the total EOR production. And so the graph here on the lower left then is number of wells versus CO2 projects, but you can do almost the same thing in terms of barrels. Oxy by far has many more projects and injects much more CO2 than anyone else. Okay, so in terms of when we start talking to the government or different government entities about sequestering CO2, one of the first questions that they ask us is, well, how can we trust, or how do we know that you know how to sequester or handle CO2 and not have it come back to us a few years down the road? And so this slide is really aimed at addressing that. What we're showing here is a map of the U.S. with the Permian basin outlined in the black. And the larger map here shows all of our different operations, including the yellow marks are where we have individual plants, individual CO2 processing plants that are part of our operations out there. And so we have over 40 years of safely handling and injecting CO2 for EOR, 14 gas processing plants. We handle 2.2 BCF of gas daily, and lots of pipelines out there. We were the first to develop MRV plans with the EPA. We are currently among the leaders heading towards developing a carbon sequestration certification with CARB, which is the California Air Resources Board. And we are in the process of offering carbon neutral or negative oil as a byproduct of permanent carbon sequestration here. Okay, so let's talk about CO2 enhanced oil recovery. The upper graph here on the right shows barrels of oil per day versus time. And the gray here is our primary depletion. The blue then is a secondary water flood oil response. And then the red is the CO2 EOR oil that is being produced from our CO2 flood. If we turn that around and we look at it in terms of recovery factors, what we can see is in a conventional reservoir, we might get 15% on primary, maybe another 30% under secondary water flood, and up to another 15 or 20% under CO2 flood. Okay. And right now we are looking at potential for recovering EOR in our unconventional reservoirs. That still is work that's in progress. Okay, so what does the process look like? What we're showing here is we're getting CO2 that's supplied from the pipeline. The source could be natural fields up in Colorado and New Mexico, or it could be from carbon capture plants that are or ethane plants where we are able to capture the CO2 out of the air and bring it to the field for injection. And so it's going into the well here. And so what we have is a series of banks that are being driven by the CO2. So an oil bank, miscible zone, we might have some CO2 here. Water, because in our case, we WAG, which is water alternating gas, most of our properties. And then typically we'll finish off with water, although in the case of CCUS, we might not do the water drive just because we want to keep as much CO2 in the ground as possible. That oil is driven to my producer, which then comes up and it's separated here in my separator. The oil goes off to sales. The water, of course, is, well, this shows the gas, but the water here is brought back over for injection. So that's where we're getting our CO2 for the WAG and the water for the WAG. The gas then is produced up to our one of our plants that's being shown here, where we can extract the gas, the hydrocarbon gas, and then NGLs for sales, and then send off the CO2 that's been extracted for reinjection. So you can see that this process, basically it's a closed loop. We're keeping the CO2 in the system once it comes in. And we typically sequester somewhere around 40% of the CO2 on each of our cycles. Okay, some basic principles of EOR. So in water flooding, we might start with an average saturation of 70% oil. By virtue of our displacement, we produce out a chunk of that oil, but a large portion of it is trapped due to capillary pressure. We have another fraction of it that is trapped by either fingering, so poor aerial sweep, or vertical inefficiencies that eventually ends up getting us back to an average oil saturation here of 44% under water flood. Now, that only gets me a recovery factor of maybe 37% of the original oil in place. If I then start my CO2 flood, again, I'm now pushing from this 44%, and with the solvent is able to miscibly mix with the oil and reduce that capillary pressure, and thereby allow that oil to move to my producer. And in so doing, then I will take, my initial saturation at a microscopic level was 38. I might take it to 24 or even closer to 0. Certainly near the injectors, it gets very, very low. And potentially end up with a remaining oil saturation on average of 36%. Now, CO2 is much more mobile than either the oil or the water. And so we tend to have much stronger fingering effects than we observed up here under the water flood. Okay. So why do we WAG? I mentioned that we WAG. Well, WAGing helps us improve the sweep efficiency by blocking due to relative permeability swings. In this case, when we inject the water, we'll try to push a pretty good slug of water in there, making the water or the area around the well mostly full of water. So rel perm, up near the end point of the water. And then as we start to inject our gas, of course, the gas rel perm is close to 0. So we're having to work it to get into the reservoir. And as we swing back and forth, between those cycles, we can maximize our sweep efficiency and homogenize that front to help improve our overall recovery of the oil. A second driver to wagging is it also helps us control the gas production and reduces the size of gas processing plant that might be needed. Okay, so let me briefly talk about some criteria. What makes a good CO2 flood? And you can see different parameters in here. Some of the really critical things are you need to have good oil saturation. Typically, we need to be fairly deep. If we're too shallow, we can't achieve a high enough pressure to attain the miscibility pressure. And so then our flood becomes very much like a very expensive water flood or regular gas flood that does not move the oil and doesn't reduce that capillary pressure that we're so dependent upon. Okay, so why do we need to forecast our anticipated results from the CO2 flood? Well, you can see here that there's a number of different things. We need to predict our sales volumes. That helps in our surface facility design, the gas plant sizing. Certainly, we need to book reserves. That's how we determine the value of the oil company, and also to present economics for our business plan for AFEs that we need to get approval for. Sorry about that. We need to get approval for so we can go out there and execute. Some other reasons are for flood surveillance and to optimize our injection strategy. So different approaches that we use or that could be used for forecasting are the three that we can see down here in the bottom left. Decline curve analysis, simulation, and dimensionless prototypes. And I'll talk about each of those here in the next few slides. Okay, so this is developing type curves or doing a decline curve analysis to forecast your performance. So one of the things that we could do is once this is very mature, we could apply a decline out here and predict how that flood is going to go. One of the things I did want to point out here is that notice how this is a decline off of my water flood before I actually started CO2 injection. And if I take that decline, then we could say these barrels above that line are my EOR barrels. But one of the things that happens is when we are injecting CO2 and particularly as we inject CO2 with water in a WAG process, our throughput or the rate at which we can process the reservoir decreases. And so we actually have an effective change in our water flood response that's down here. So really the overall EOR response is this larger wedge that we can see here. Okay. But when we come to applying DCA, you can see that if I was trying to apply DCA, I've got many years here before I actually get to something that might be stable enough that I could actually do a decline curve fit through it. And so in the meantime, I'm kind of waiting on that oil response, right? Further, if I'm developing this on a type curve to just estimate using some analog response, some of the things that we're ignoring are the geology, the pattern shape, pattern size, and so this becomes a little bit of an issue. The figure here is talking about simulation model construction, and of course, a simulation model is a compendium, integration of the petrophysics, the geology, the production engineering, the reservoir engineering disciplines to develop a model that is predictive. And so, of course, in the petrophysics, we're bringing in our core data, our cap pressure data, and the logs to generate inputs to our geologic model. Those, of course, we've picked different tops and distributed the fluids in that model, distributed the properties and the fluids in the model. From the production engineering side of things, we are looking at connectivity or how the wells are completed. And then from the reservoir engineering side, we are looking at the PVT, the relative permeabilities, and of course, putting that all into a simulation model. One of the big challenges that is still facing many of the simulators is the development of a second or more liquid hydrocarbon phase. That's shown over here on our pressure versus mole percent CO2 diagram as this phase envelope where you have multiple liquid phases that are appearing here. And so that tends to cause instabilities in our convergence. As the models find multiple routes that they are really not very well geared to handle. Now, a second challenge, of course, is also from the relative permeability and the hysteresis. So each time we add things like these complications into it, that tends to make our overall solution a little bit slower and gives us some challenges there in terms of run times and things like that. Further, as I mentioned, you've had hysteresis that can cause issues with convergence. It's not always used, but we can incorporate gas trapping into the models through higher Corey exponents or gas trapping parameters, and those parameters may be all part of that history matching process. An alternate approach is to approach this from a dimensionless scaling perspective. And when we talk about dimensionless scaling, a very common dimensionless number that we use in the petroleum industry is the recovery factor, which is, of course, your cumulative oil in place divided by the oil cumulative oil produced divided by the original oil in place, right? And so what we're showing here is a recovery factor on the y-axis versus dimensionless injection on the x-axis. And again, in a similar manner, we're using the cumulative volume of water and CO2 in reservoir barrels divided by the hydrocarbon pore volume. So all of this is using the hydrocarbon pore volume to normalize the response function. Okay. On the graph here, the green dots are actual history, and the red line is where we started our CO2 flood. So during this time frame here, we are injecting water. And one of the challenges that we have is I need to be able to predict or estimate how much of this oil is coming from my CO2 injection. And the only way I can do that is I need to come up with a forecast of what would have happened here with my water flood. And so if I take this equation that we call it an A and C fit, and I fit this early time data, I can get the blue curve out of that, and then the difference between that blue curve and the actual data, or I can extend the actual data and come up with a EOR volume that we will see from our injecting CO2. If I take the throughput or the percent of hydrocarbon pore volume injected per year and apply it to this graph that's on the left, I can convert that over into a rate versus time graph, as you can see over here on the right. In this case, again, the green dots are historical data. We have now fit, so this blue curve that you're seeing here is the fit and the extrapolation of that water flood behavior. So that's the dark green curve that you can see here. I will talk about the prototypes in just a minute, but basically our forecasting that is coming from this difference then is this light green curve. And of course, the sum of the dark green and the light green curve gives me the black curve, or that's my total oil response to this field. Okay. So in this case, this is a dimensionless prototype that we're seeing. And so what I want to point out is that what we've done is we have now created a new zero, starting with the CO2 injection. So that gets me by zero on the injection scale. So again, cumulative total injection or dimensionless injection down here on the x-axis versus the EOR, DEOR or dimensionless EOR curve, the CO2 that's been injected, so that's the magenta curve, our CO2 that's produced, and then the water that's been injected. Okay, so that group of curves helps define what is going to be the production response or the injection and production response to injecting the CO2. Now, as you can imagine, I'm using this water flood curve and the difference between it and the red to define this green curve that is my DEOR response. We also do a similar process for the CO2 production response, in that we will calculate what is that water flood gas production, and then by difference get the dimensionless CO2 production. Okay, so why would we use dimensionless scaling methods? Many times when we are managing our floods or forecasting the floods, we need to iteratively schedule the CO2 volume that we need to purchase and that we need to handle to be within our facilities and CO2 supply limitations. And those tend to be iterative type scenarios or functions. And of course, doing that in simulation, we could do that, but it would take a very long time to be able to do that. And this is a flow chart of the process that we use for a tool that we call DoScale. And so here's a calibrated simulation model, geologic model, the laboratory data, and our production data that all combine to get us a calibrated compositional model. Now, if I go out there and I run that simulation model, and I run it for just water to begin with, and then I run it and I say, okay, now I'm going to start a CO2 flood, and I take the difference of those two models, I can derive this EOR prototype. We've already talked about getting our regression fit of the water flood. That's what we're doing on the prior scale. And of course, our throughput, our injection rate, the percent of hydrocarbon pore volume that we've injected per year. And if I bring those three inputs together, then out of this program, I'm able to generate a set of curves that describe the oil and the gas response to the CO2 and water injection. Okay, so that allows me to, this DoScale program allows me to run a large number of options very, very quickly. It allows me to consider and roll up the forecast at multiple levels. So I can do it by facility, I could do it by project, or we could do it by areas that have similar geology or performance, where we may want to go through there and evaluate relative performance for our surveillance process. Okay, so this is an example where the prototype was developed and fit for a an area that has 349 patterns. Now, in this particular case, we're not using the same prototype for all of those patterns. We have multiple prototypes, but this do-scale program allows us to roll them all together, so we're able to see how did our data fit, both historically and then as the forecast goes out into the future. And so we can see here a very good fit both on the dimensionless world as well as in the overall production world. Okay. So when it comes time to do surveillance, this is a typical setup that we have for our surveillance process. Typically, we will have the geologist, a production engineer, the reservoir engineer, our production tech from the field, and an injection tech from the field, all involved in the reviews. The geologist here on this particular day has presented a cross section of one of the patterns, so you can see the producing wells out here on the side, and the injection well here in the middle. And then the rings here are basically injection profiles. So that's a log that we can run to help us identify what zones are taking CO2. And so thereby evaluate, what's getting flooded, what's not getting flooded. In the middle, we're showing different dimensionless analysis plots or maps that allow us to evaluate and compare different patterns. And then finally, over here on the right, we're seeing the dimensionless EOR versus dimensionless CO2 injection, which again allows us to see and evaluate, are we doing as well or better than our prototype? In the case maybe of this group of patterns down here, we might highlight that group and identify, well, where are they located, and start to evaluate what's going on with them, that they're underperforming the rest of the patterns. The three main focuses that we take on when we're doing surveillance is to maximize our recovery factor. So we're looking at the vertical sweep efficiency, the aerial sweep efficiency. Displacement efficiency, we typically don't have a whole lot that we can do with that as long as we're above minimum miscibility. But that is something that's always in the back of our mind when we're doing our surveillance, particularly if our reservoir pressure on a new flood, or our reservoir pressure is not really above or very far above the minimum miscibility pressure. The second thing that we're really focused on is maximizing our throughput. So again, throughput is the speed at which we're able to process the reservoir. And then third is maximizing the value that we are getting from our CO2 that we're injecting. So in this case, the metric that we're using here is the net present value at 15% per MCF of CO2 that we are injecting. And the deliverables that come out of these surveillance reviews are injection and reservoir management strategies. In other words, where do we need to work on wells? Do we need to change the way that we are injecting, maybe to drive new streamlines or things like that? We are looking to flatten our base production decline, and finally to optimize our cash flow. So in some cases, especially, we just recently came through a tremendous price drop, and part of that was optimizing our cash flow. And so in some cases, it made more sense to cut back or essentially stop injecting fresh CO2, or even in some cases stop injecting CO2 altogether in some areas of the fields, and to optimize our cash flow and to carry through on the performance that we were getting out of the oil from the previous CO2 that we'd injected. Okay, so in summary, simulation gives us a lot of flexibility. One of the things that simulation does that we can't do in any of our other tools is if I have very different reservoir characteristics or different pattern configurations, maybe in some of our cases we've gone to slant wells, whereas in a lot of cases our wells are vertical. But in some cases where we've gone slant or horizontals or things like that, maybe I don't have a good analog. And so I need to do that in simulation. I need to look at that. Now, the downside to simulation is that it is very time consuming. You need a lot of runs for history matching. Each scenario that you want to evaluate needs a new run, even though we're maybe starting from a restart. But if we're in a full field model or a large sector model, that can take hours to run or even days. Many times it requires a lot of technical expertise to set up and run the models effectively. In some cases, and particularly with some of our stuff here, we need to recognize that the forecast can be optimistic. They might, again, the simulator is treating things as if it's a kind of an ideal world out there. In some cases, we have fractures or from previous well completion strategies. In some cases, we've got where they nitrous shot wells or did other stimulation techniques that have created additional fractures that create short circuits to between wells, and sometimes that is at a detriment to the ability of the well to flood the reservoir between the two wells. And of course, that's not something that's typically baked into a simulation model. But it is the only approach that we have for new floods, for very complex situations, or for developing prototypes in areas where we don't have a good analog. Simulation typically is not really all that good for surveillance because the forecasts are very deterministic in terms of what did you inject, and of course what you inject then drives what ends up being produced. And so it's hard to make those comparisons because you're never quite looking at things in terms of apples and apples. The dimensionless prototype, it is limited by analogs. You need either similar reservoir conditions, you need similar pattern layouts. But on the plus side is that you can get a lot of runs in a very short period of time. You can explore gas supply and processing scenarios very quickly. We can evaluate multiple WAG scenarios for economic optimization. And in fact, we do that quite frequently. And typically it's seconds to minutes to run. And in fact, we use this approach to successfully forecast 33 of our units that have over 2,700 CO2 flood patterns. And this also provides direct reservoir performance in our surveillance tools. Okay, a few takeaways. First, Occidental is committed to using our global leadership in carbon dioxide management to advance a lower carbon world. We are the number one producer in the Permian and DJ Basin. We're number one in CO2 EOR projects around the world. We are, independent producer in Oman and the number 4 producer in the Gulf of Mexico. And right now we are working very hard to be the first in carbon dioxide management to advance a lower carbon world. And I think you can see that, from our expertise and experience with managing CO2 floods, that puts us in a very advantaged position. Finally, and a quote from Larry Lake: "Best place to find oil is in an oil field." How true. It's the easiest place to find oil, right? Very important. You need to understand the physics of the process and then apply those physics in a meaningful approach. Always be willing to take on new challenges, new roles, test new ideas. If management comes and asks you to go try something new, give it a try, right? Teamwork is much more powerful than I work. And you know, there's another saying out there that there's no I in team, and that's very true. You know, bringing a lot of brains together sure makes things work very powerfully. The interactions and the opportunity to share and build on ideas is really great. Encourage you to invest in your career, your life, work to overcome the obstacles, and try to learn something new every day. And with that, I will open up for questions.
David, thank you very much. We really appreciate the presentation and wonderful takeaways at the end too. What I want to do was I want to ask, first of all, are there any students who would like to ask a question, graduate or undergraduate students? I'm looking at the participant window. You could put a hand up. You could just unmute yourself. All right, any faculty like to ask a question? Dr. Mohanty.
David, very nice talk. Why do you think foam has never made it in these CO2 floods?
That's a good question. One of our big challenges, and to be honest with you, I think you know, we did try a foam project in one of our CO2 floods about 2016 and forward, and we were working with Dr. Nguyen, and one of the challenges we got into, I think it would be a good approach, a good process to use in areas where we have high permeability. But one of our challenges is that we tend to operate our fields right at the edge of or just under fracture pressure to maximize that rate throughput. And so when we hit it with this foam, it tends to reduce our throughput so much that we actually lose oil production because it slows down the flood so much. Is there room for optimization in there? I bet there is. But it does pose a challenge, because to get the better sweep, you need the pressure drop, but the pressure drop creates you know, economic challenges.
Another question, you guys are trying to do work with carbon engineering to get the direct air capture of CO2. How expensive is that compared to your normal CO2 that you get?
Let's just say without the carbon credits and tax incentives, it wouldn't be a starter.
But is it like 5 times or 10 times? How much?
To be absolutely honest with you, I haven't seen a cost for it, but of course it does. I mean, it's costing in the billions to build the plants, right? So you can, you know, from a capital perspective, it's very expensive.
Thank you,
David. This is Larry Lake. First of all, will you make your presentation available to us?
Let me run it past my managers to see if they'll let me share. I'd ask for it to share it this way, not through shall we say, an electronic format, or not through the.
Thanks for the credit to the quote. For some reason, I always sound like a lot more smart when somebody else quotes me than when I say it myself. I don't know how that works, but it was a good summary of models, and I agree with virtually all of it. I was just wondering if you could speculate on how these things would be modified if you were doing just carbon storage, not trying to recover oil.
Well, one of the assumptions that I didn't really bring up in the dimensionless process is we assume that we are in an IWR at 1 or very close to 1. Of course, in simulation, and we are looking at pure sequestration as well, but that the economic value of getting oil out and is so much more, there's so much more incentive to doing it that way than the pure sequestration. I think, through simulation, you could do it quite well. Okay. The challenge that we've seen in a lot of cases is that if you are dealing with a one-off or a brand new development, i.e. aquifer sequestration, you don't really have the history to be able to say that I have a seal. In a dimensionless world, we would probably have to go back and rethink that one completely. As I said, there's not really a production function, I think, Larry, out of that, right?
No.
And so that's one of the challenges. I mean, you could say I'm just doing a pure material balance. I'm injecting, I'm not taking anything out. And so I just need to watch it and see how long it takes my pressure to build, So I think you could do something like that through a material balance approach.
Unless there was a carbon tax somewhere.
Not sure I understand the comment.
Well, you said there's no production function on that, and there wouldn't be, but unless there was a carbon tax, and you could get a little bit of money for how much CO2 you inject.
Right. And I mean, there is some incremental carbon tax, or not tax, but benefit from sequestering or pure sequestration over a CCUS type environment.
Yeah.
But even there, I mean, the value of the oil tends to outweigh that. If you can do EOR, that's probably your best first option, right?
Okay.
Awesome. Dr. Delshad, you had a question?
Yes. Hi, David. Thank you for your presentation. Actually, I have two quick questions. What is the role of tracer testing within Oxy CO2 projects?
We have done them. It tends to be fairly expensive, and in some cases, the CO2 itself is a nice tracer. If we can look at our WAG sequences, and if I have enough difference in the WAG sequence, sometimes I can start to piece together connections without actually having to go spend the money on doing the chemical tracer type approach.
But do you believe maybe tracer testing may have a bigger role for CO2 storage projects?
That is very possible. The problem is that it's almost like a false negative, right? If you don't see it, you're not sure that you actually captured it. But on the other hand, if you do see it, you definitely know you got a problem, right?
Right.
So I think there are some pluses to it, but we probably have to figure out how to structure that one economically, right?
And you mentioned that almost 99% of CO2 can be stored, but on average, part of your CO2 EOR projects, what is the estimate of CO2 remaining in the reservoir after you basically abandon the field?
Okay, so we would, if you look at the dimensionless CO2 produced versus CO2 injected, typically we would run it to where we have basically sequestered or captured about 40 to 60% of that. Okay, but what you need to understand is I'm cycling it.
Yes, that's right.
Right. So I put some in, I get a little bit out. I have to put it back in. and I put in some new stuff with it, and then a little bit more comes out. But at the end of the day, I'm going to put that last little bit back in the reservoir, and then I'm done. Right?
Okay.
So I can get there. It's just because a lot of it is the cycling, and it's the progressive retention of the CO2.
Okay. Thank you very much.
Sure.
Professor Lifesky, you had a question?
Yes, thank you, Michael. Great presentation, David. I would like to follow up on Professor Mohanty's comment about carbon engineering. So I think I read somewhere in the news, I think it was an interview with the CEO, that the current price is around $600 per ton, and they want to reduce it to 100, which they seemed not very optimistic at that time. I think that was about 6 months ago. So I'm not sure how accurate those numbers are, but at least this is what I know. My question to you, David, is have you tried actually to look at Svante or any other company? Svante is another company from Vancouver, British Columbia in Canada. That are, yeah,
I have to be honest with you, I'm not really on the plant side of things. So I don't know what all they considered at that time. I do know that at this point, Oxy has a pretty strong agreement with, oh gosh, can't remember.
Carbon engineering.
Yeah, it's carbon energy. Yeah, that make the direct air capture plants. And I know that they did a pretty good chunk of effort to evaluate a couple of different methods, and this seemed to be the one that they thought had a lot of promise. And I think they had a small plant up in British Columbia that was actually operational. And so the next kind of scale up that we're aiming for is to take that concept and put a couple out in near Midland.
All right, thank you very much for that. And my second question is, I'm not sure I heard anything about downhole telemetry for monitoring. Are you using anything at all to make sure that your CO2 is going up and down where you want?
We use injection profile logs. So
all right.
Again, we can get in and log the wells on a periodic basis. Having and I assume you mean fiber optic or something like that to monitor. It's just, let's say it's about 25 times the cost. So, at the end of the day, it all comes back down to, okay, how can we most effectively do this measure, right?
Very good. Thank you very much, David.
Sure.
David, I'd like to ask one question. Early on in your presentation, you talked about the opportunity to have net negative by using non-fossil sources of CO2 for injection. Can you discuss a little bit around that? What would that source be?
Okay, so it'd be taking CO2 out of the air that shall we say was burned or was emitted from different processes, be it an ethane or ethanol type plant, or just the cars and whatever driving around, and capturing that CO2 and re-injecting that into the ground. Okay. So if I can put more carbon into the ground than what I'm getting back out in terms of oil, that gets me carbon negative.
Okay. So direct capture from the atmosphere. Very cool.
That's it. Yeah. And I thought I had a slide in my deck that was with our DAC plants, but I guess I missed that one.
Any other questions? All right. David, thank you very much for spending the time with us. We very much appreciate you sharing your expertise with us.
Well, pleasure. And thank you so much. Good questions. really enjoyed getting to see so many of the professors there. And yeah, if people have questions or whatever, they can send something to my email, and I'll be more than happy to respond.
Awesome. Well, thank you very much.
All right.
See you, Dave. Bye-bye.
Bye, guys.